very essential technique or routinely used a method by the researcher. So today we'll study the basic principles and some examples and how to analyze the mass spectrum or how uh, mass spectra, the mass spectrometry measurement works. So one thing I must add at the very first that we are adding the term mass spectrometry, not spectroscopy. So what we do, we use the term UV spectroscopy, infrared spectroscopy, NMR spectroscopy, MOSBA spectroscopy, etc. But we are using the term mass spectrometry, not spectroscopy. This is because that the spectroscopy means the light matter interactions. That a light is going to interact with the matter, uh, let's say organic molecules. The molecules is going to the excited state, and when it comes back, it emits some lights, and from that point of view, it is called spectroscopy. But in mass spectrometry, you will see that such kind of phenomenon do not happen. We hit the molecule by high energy electron beam or something else, and the molecules breaks, and the broken fragments reach to the detector, which is not that kind of things. The during the mass spectrometry analysis, the molecule is going to be excited. We break the molecule. That's why we do not use the term spectroscopy here. So we use the term mass spectrometry. So it is very openly said by a lot of students mistakenly or unknowingly mass spectroscopy. So we never use the term mass spectroscopy. It is mass spectrometry. Okay. So this is an interesting technique that the mass spectrometry by electron impact. So what we do during this kind of methods that during electron impact mass spectrometry, the molecule is bombarded by highly energetic electrons. And what happens if we bombard the molecules or if we hit the molecules by high energy electrons? That electrons will knock out weakly bound another electrons from the molecules. Okay, so basically what happens? So in this method, what we use, let's say we have a molecules here. Let's say this is the molecules. So we bombard the molecules very high energy electrons, very high energy electrons. And what happens if we hit the molecules by high energy electrons? The electron knockouts another loosely bound electrons. So this electron removes from these molecules, and this is what kind of electron? This is loosely bound electrons. So what will happen? So the molecule will end up with a radical cation because one electron is removing. So one positively charge will be generated. That's why it's a radical cation. Radical cation. So this is very highly interesting term or a widely used term during mass spectrum analysis, the radical cation. So what happens? That when we bombard the molecules by very high energy electrons, the electron knockouts another loosely bound electron. So basically this electron loosely bound, loosely bound. That's why it's removed from the molecules or knockout from the molecules and it end up with a radical cation. Okay, now we'll see what happens. Before that, we'll compare the phenomenon. Okay, so let us understand what in terms of what happens in terms of some physical phenomenon. Now let's come back to a real world, from molecular world to a real world. Let's think. So this is a wall. Let's say this wall is made of some bricks wall. Now we are hitting this wall by another bricks. So the bricks will hit this wall. As a result, what will happen? This brick will not be stick to the wall, and the loose. Let's say there is another loosely uh, bound bricks. Means this brick was loosely attached to the wall, loosely attached to the wall. So these bricks will go away, go away. So what we get? So we will have, this is the vacancy, and that's the phenomenon. Means there is a vacancy in molecule also in terms of electrons. So what these bricks will do? The bricks that goes away, that also have very high energy. So we'll later discuss the fate. So right now we can correlate very easily that the comparing or taking in mind the real scenario, that if a brick hits a wall, a loosely bound bricks goes away from the wall. Similarly, if a high energy electrons hits the molecules, loosely bound electrons go away. As a result, the molecules will be ended up with a radical cation. Now, what happens? The mass spectrometry machine or analyzer is designed such a way that let's say we have many radical cation here that has been generated upon hitting with high energy electrons. Now their pathway are designed in such a way that it has been magnetically and electrically pushed towards the detector. So here we have the detector. Detector. So this will be rushed towards the detector. So here magnetic field and electric field are applied such a way that the positively charged will rush toward the detector, will be detected or will be recorded. So it is very clear that to be to become detectable, its mass spectrometry or in mass spectrum analyzer, the molecule must have to be charged. The molecule must have to be charged. Molecule must have some charges. So what happens? So if the molecule is uncharged, it will be never reach to the detector because the pathway is driven by electric field and magnetic field. So uncharged molecule will not be detected by the detector. So uncharged molecule will not be detectable. Okay, so just I am summing the statements what I discussed. For example, we have a molecules. We hit the molecule by high energy electrons. What that electron will do? That electron will knock out our loosely bound electrons. So the molecule will be converted into a radical cation, and that cation will be rushed toward the detector as its pathway is driven by magnetic field and electric field. So it will be detected. So we are correlating this phenomenon by, or we are visualizing this phenomenon by real world phenomenons that the brick, if a brick is thrown towards the wall, that brick will just displace another bricks which is loosely bound in that wall. And what that brick will do, or what this high electron will do, that we'll later discuss. We'll discuss later. So this is. So now let us discuss which type of electron displace. So loosely bound electron displace. Loosely bound electron is knockout by high energy electrons. Let us visualize the things. Let's say we have a carbonyl compounds. Means here these two are lone pair. Rest of the all the things are inside bond. So if we hit these molecules by, let's say we hit the molecule by electron, then one electron will go away. Means this bond, this lone pair will go away. So as a result, what we will have one electron here. So basically, it's a radical cation. A radical cation, as lone pair is loosely bound. Now we are visualizing that which electrons is going to be knocked out by the upcoming high energy electrons. Lone pair is loosely bound. Similarly, let's think about ammonia. So it has three bond pair and one lone pair, and it has been hidden by high energy electrons. So one electron will go away. So it will end up with dot plus a radical cation. So here one condition is there. If the energy of the electron that hits the molecule is not too much high, then these molecules will reach to the detector at its radical cationic state if too not high. What happens if the energy is very much high? What happens? We'll discuss this later on. So up to this we have visualized very nicely. Then we'll move to the next part. So, so what happens in the first slide? What we discuss, if the energy of the electron beams is not too high, then the radical cation will survive. So case 1, if energy of incident electron beam is not too high, too high in what? In energy, then the radical cation, radical cation will survive and will reach to the detector and will reach to the detector and will be recorded. Case 2, what happens if the energy of the incident beam is too high? What happens if the energy of incident electron beam is too high? Beam is too high. That's the question marks. So the extra energy, as the energy is too high, so by this energy, its knockouts on electrons, it generates a radical cation. So the extra energy will be dissipated by the fragmentation of the radical cation. So we have a molecular ion. So it has been heated by electron, that is high energy electrons. Now we easily understand or visualize it has generated a molecular radical cations. It will be it will reach to the detector if nothing happens to its no means if it survives. If it survives, then only it will reach to the detectors. When it will survive, if the incident the energy of the incident electron beam is not too high. If it has a very high electron, then again it will going to fragment it. Means it is going to fragment into m dot plus y plus one radical and one cation. So what will happen? So radical, this is uncharged, means it will not be detected, no record found, and cations charged, so it will be detected. Let us visualize by this example. So let's think we have this, let's say molecular ion molecules. So after hitting by a high energy electron, means very high energy electrons, it will produce radical cation because one electron goes away after the heating. So it's a radical cation. Now the energy is very much high. So it is going to fragment into x dot plus y plus, means charged, and hence will reach to the detector. Why would it reach to the detector? By the electric field driven pathway, or through electric field driven pathway, and will be detected, and it will not be detectable. And why we are studying this kind of theory in very details and just taking time, because nowadays the question pattern is going to be changed. So what is happening in each and every chapter, we should have clear understanding. That's why we are basically, because we don't know from which part which type of question will come, the pattern is going to be changed. That's why you need clear understanding. That's why we are just discussing on the very basics. So right now what we understand that two things. One is that if the high energy electron hits a molecules, a loosely bound electron from this molecule is going to be go ahead. So molecule will be end up with a radical cation. Now the question, which type of electrons is going to be where? The loosely bound electron is going to be from the molecules. Means the lone pair. If a molecule have a lone pair, if a molecule have a lone pair, then the one electron from the lone pair is going to be where? Now we have a radical cation. Now what will be the fate of these radical cations? This depend upon two things. So if the energy of the incident beam is not so high, then the radical cation will survive, and that will rush towards the detector by a path that is driven by electric field and magnetic field. So number two. So what will happen if the energy of the incident beam is very high, then the extra energy will be dissipated through the fragmented of the radical cation. As a result, the radical cation will be fragmented into one radical and one cation. The radical is uncharged, so it will not reach to the detector, will not get any mass from this radical part. For the cations, it is charged, so it will rush toward the detector and will get the mass of the cationic part. So now, so we understand that. Okay, so what we understand? The radical cation fragmented into two parts. Okay, let's before that let us visualize one examples. So we had this as molecules. After electron bombardments, it's formed a radical cation, and the radical cation is going to fragment into this radical, which has molecular mass or the mass value 71, and the cationic part will be 43. So 71 will not be detectable, and this will be detectable. This will be detectable. Detectable. This will not be detectable. So let's see. So this is the result. See, the base peak is 114. So why 114 is detectable? Because these molecules, that is 114, so it's a radical cation. Radical cations means is a positively charged, it will be detectable. Look, here we have a mass 114. So this mass is for this part plus dot. If this fragmented, this is uncharged, so 71 will not get in the mass spectrum. Look, in the mass spectrum, it has 71, but later we'll discuss why this is not 71, it's something different. But here we'll have a charged, that is 43. So the highest intensity is 43. This part is for this one. Now, from here, we'll learn two things. That the highest intensity, the most intense peak, that is intensity 100%, that is called base peak. So this is the base peak, and this is the just molecular ion peak. This is called molecular ion peak. Let's say in lab we have synthesized these molecules. We are going to be confirmed by whether this molecule is formed or not. First, we'll try to find out the molecular ion peak. If it is found, we are very lucky, it's okay. We find, okay, 114 is there, so molecule has been formed. And then if we don't get the molecular ion peak from the spectrum, then we'll go for whether the mass of the fragmented is going to be uh, just find out in the spectrum or not. Here we find something mass, so means it has been formed. And one thing that we must always ever remember, that the from the intensity of the peak, from the peak intensity, from the peak intensity, we never can say that the amount of the molecule, we never can correlate the amount of the molecule formed from the peak intensity. Means, for example, we have a peak that intensity more. From that peak, we cannot say that molecule has been formed more. So peak intensity cannot quantify the molecules. quantify the molecules. Why we are discussing this chapter again? Something though a lot of students are doing projects and will go to the PhD very soon. So there, just we need this just to dictate. That's why we are going that much details and slowly. So this will remember always peak intensity cannot, not only cannot, never can quantify the molecules. So let's say this molecule was 100% or 95%, another some molecule was 5%, but we are getting 114, but very small. It doesn't say that as 114 peak is very small, the molecule has been formed. Just to detect whether the molecule has been formed or not, we take the help of mass spectrometry. So another things, here we put the relative abundance in the y-axis and m by z in the x-axis. Always charge has been incorporated into the mass because it is the charged species that is going through the detector. So x-axis always m by z.